In this video, we are going to learn how to actually calculate the eigenvalues and the eigenvectors for any matrix that I give you, or that you are given. So, how do we do it? The way is that we start with the definition of the eigenvector. Matrix A times the eigenvector B is equal to eigenvalue lambda times eigenvector B. That's the definition of an eigenvector. Now we do some algebra. So we bring lambda V to the left-hand side. A times V minus lambda V equals 0. And now I want to factor out vector V. But remember that in order to do this, we need an intermediate step here, because we cannot do A minus lambda, because A is a matrix and lambda is a scalar. But we can say that our vector V is equal to the identity matrix times V, right? Because the identity matrix leaves vectors unchanged. So we can always write this. And now we are ready to factor out V. So we can say that A minus lambda I, identity matrix, times vector V equals 0. Okay? So, starting from the definition of an eigenvector, we have arrived to this alternative definition, which is much less intuitive, but at the same time is much more helpful, because this allows us to calculate the eigenvectors. Now let's think about what this is saying. So A minus lambda I, what is that? So for example, imagine that matrix A is a matrix given as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? What would matrix A minus lambda I be equal to? So it will be equal to this matrix minus the identity matrix multiplied by lambda. So that would be the matrix that has lambda, lambda, lambda in the main diagonal and zeros everywhere else. That would be lambda times I. And therefore A minus lambda times I is equal to this matrix 1 minus lambda, 5 minus lambda, 9 minus lambda. Those will be the values in the main diagonal, and the rest of the values are unchanged. Okay, so that will be A minus lambda I. So we know that this matrix multiplied by V is equal to 0. So that will give us the eigenvectors V and the eigenvalues lambda. Now, how do we begin solving this? So remember, this A minus lambda I, this will be a matrix which depends on lambda. Yeah, so this will be a matrix that depends on lambda. But remember, when you are solving a system M, matrix M times vector V equals 0, we learned in the last chapter of solving linear system of equations that two things may happen. Either the determinant of M is not 0, in which case there is a unique solution given by V equals 0, and this is unique. Or the other alternative is that the determinant of matrix M equal to 0. And when that happens, we know that V has infinite solutions. And how are they written? They are written as alpha times a vector plus beta times another vector plus gamma times another vector. Do you remember this? So this is basically the null space of matrix M, because this equation is the definition of null space, yeah? And the null space of matrix M is always a linear combination of n vectors, so from 1 to n. So this null space, normally when calculating eigenvectors, the most common thing that happens is that the number of vectors in the null space is only 1. So the nullity of matrix M is only 1. And this will correspond to the eigenvector. But sometimes the nullity is more than 1, and we have more than one eigenvector. But now please remember that M is a matrix which depends on lambda, right? M is a function of lambda. So we have it here written. M is a function of lambda. Therefore, the fact that the determinant of M equals 0, it will depend on the value of lambda. So from this equation is from where we will calculate the eigenvalues. So which values of lambda achieve this? And once you know which values of lambda achieve this, you can calculate which vectors are solution to that equation, to this equation, for those given values of lambda. And those will be the eigenvectors. So always we have two steps. So let me write them explicitly, because maybe this is too much in a single block. So let me separate and write explicitly the two steps. So the first step is you find the matrix A minus lambda I, and this is a matrix that depends on lambda, and you calculate the determinant of this matrix. And you force this determinant to be equal to 0, okay? So when you calculate the determinant of this matrix, for example, imagine we are calculating the determinant of this. So obviously this determinant will include lambda in it, right? In fact, it will be a polynomial that includes lambda, okay? So this polynomial will be a function that we call the characteristic polynomial. So it will be p of lambda equals 0. And this is called characteristic polynomial. P of lambda of the matrix A. So now it's a polynomial, and therefore you can always factor out a polynomial into its roots, right? For every polynomial, you can do a factorization. So how would that look like? So that would look like this. It will be lambda minus some number, let's call it lambda 1, times lambda minus some number, let's call it lambda 2, times dot 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 lambda minus some number, let's call it lambda n. So those will be the n roots of the polynomial, so we can write them as these factors, and this will be equal to 0. So of course, the values of lambda that solve this equation are the values of lambda equal to lambda 1 or lambda 2 or lambda 3 or up to lambda n. So the eigenvalues will be lambda equals lambda 1, lambda 2 up to lambda n, the roots of the polynomial, of the characteristic polynomial. So by finding these eigenvalues, we will know that we have found the values of lambda such that we are, in this case, the determinant of m equals 0. So knowing that lambda has now each of these values, so now for each of these values, we know that we are in this case. And therefore, our aim is to find the solution to vector v. And those will be the eigenvectors associated to each of the eigenvalues. Okay, so that will be step 2. So the second step is find the eigenvectors for each eigenvalue. So let's write explicitly how this step would look like. For each eigenvalue, lambda I, so we have to repeat this n times, okay? For each of the eigenvalues, we set lambda equals lambda I. So we now have a matrix A minus lambda I times I. And therefore, A minus lambda I times I equals 0, times V equals 0. We know that this will have infinite solutions because the determinant of this matrix is 0. And therefore, we know that this system will have infinite solutions for V. Okay? So we know that this will have infinite solutions. So we solve the system. For example, you can use Gaussian elimination to solve the system. Although you can solve it in any way you prefer, okay? So after solving the systems, the solutions will look something like this. V equals alpha times a vector plus beta times a vector plus dot 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 gamma times a vector. And these vectors here, these vectors will be the eigenvectors associated to the eigenvalue lambda I. Okay, so that will have been for lambda 1. Next we repeat it for lambda 2, and we repeat this second step. We substitute lambda equals lambda 2, and we solve this system, and we find a new set of solutions. And those new vectors will be the eigenvectors associated to lambda 2. Then we repeat. We do it, we set lambda equals lambda 3. So we solve this system. We know there will be infinite solutions because lambda 3, remember, all these lambdas make the determinant of this matrix equal to 0. They were found explicitly for that. So therefore, with lambda 3, again, this will have infinite solutions because the determinant of this is 0. And we will find the solutions again, something like this. And those will be the eigenvectors associated to lambda 3. And so on until we end going through all the roots of the characteristic polynomial. Okay? So I think this is the theory, but of course, you won't really understand it until we do some examples. And that's exactly what we are going to do next.